section 1.3, we are now ready to start talking about how we graph equations. Basically, we are looking for a visual representation of an equation. And in particular, we're going to be looking at equations in two variables and how we graph those. This is going to be the most basic way to graph an equation, and this is the same technique that's kind of like the basic first try at graphing an equation that we use all the way throughout mathematics. We will eventually start looking at graphing equations by studying the type of equation that we're looking at, but in this section we're going to be doing the same approach that your graphing calculators, or maybe your computer, if you have a graphing utility on your computer, will use to graph those things. It's going to be using something called a value table. We're going to pick values, plug them in, and see where those points show up. And in particular, we are going to be looking at the graphs on something called the rectangular or Cartesian coordinate system. So let's begin by taking a look at what we mean by a rectangular coordinate system. However, before we jump into defining the aspects of the coordinate system, let me give you an outline of the essential concepts that we will cover in this section. We're going to begin by plotting points on the rectangular coordinate system. Then we'll follow that by actually graphing equations on that coordinate system. And last of all, we want to be able to interpret graphs that are provided for us. The rectangular coordinate system gives us a very powerful tool for visualizing equations, especially equations in two variables. Basically, what the rectangular coordinate system is it is two number lines. Okay, we've already looked at number lines in previous sections, so we are familiar with the concept. But if you take a number line, so I've got a horizontal line right there, and I take a second one but make it vertical. Okay. Of course, you can draw these easily by hand. There's no necessity for this class that you be able to draw them with a straight edge and get them exactly correct. A rough approximation, hand drawing is just fine with me. But basically, the idea is that you have what's called an x-axis, your horizontal axis, and you have your y-axis. Now, in general, we think of x as the independent axis or the independent variable, while y is our dependent axis or our dependent variable. And we'll see where those terms show up later on. So you have, in the same way that our number line that we covered in a previous section was, we have unit lengths on that number line, and we have the positive going to the right, and we have it going negative in the left direction. For the vertical one, which we haven't looked at vertical number line, we're going to have that up is positive, 2, 3, 4, and then down is negative. Notice how this particular setup basically covers the entire plane. That is the flat surface on which I've drawn these two. In fact, it would be the surface that is your monitor, right? That flat surface. That is the plane that is now covered by these axes because they go off infinitely in both directions. The two number lines divide the plane into four different pieces. We call those pieces quadrants because there are four of them. We would call this quadrant, typically we refer to this as quadrant 1, this whole area up here to the upper right. In this quadrant, everything is positive. We call this quadrant 2. We actually label them in a counterclockwise direction just by convention. This would be then quadrant 3, and this is then quadrant 4. And the last particular aspect of this I want you to note is that the point at the very center, right there, is called the origin. Okay? And this is the rectangular coordinate system. Let's talk about how we plot points on the rectangular coordinate system. Note that in the ordered pair x, y, the x represents the horizontal location of a point in the rectangular coordinate system, and y represents a vertical direction or vertical location of that point on the rectangular coordinate system. So allow me to redraw our coordinate system There's my y-axis, here's my x-axis. If there is some point in the plane, say this point right here, and I want to describe its location, what I will do is I will look at its horizontal distance, meaning this distance right here from the origin. Okay, that will be the x-coordinate of that point. If I project this thing back to the y-axis, its height, either thinking of it as this distance right here or this distance right here, those distances are the same. That length, if we call it y, is the y-coordinate. So the coordinates of this point would be x, comma, y. Let me give you some numerical examples. We are asked to plot the following points on the rectangular coordinate system. We are given A is the point 2, 5, B is the point -1, 3, C is the point -1.5, -4.5, and D is the point 0, 2. In every case, please note that the first coordinate is always the x and the second coordinate is always the y. That is why it's called an ordered pair, because the order matters. Let me begin by drawing my rectangular coordinate system. Here's my y-axis, here's my x-axis, and now I need to mark out units in the x and y direction. So 1, 2, 3, 4, 5, 1, 2. Notice left would be negative, of course. Up is positive. Down is negative. Alright, now let's plot these points. I'll do those points in, say, green. So where's the point 2, 5? Remember, the x in this case would be 2, and 2 would then represent the horizontal location. So that means I'm going to go positive 2, which means to the right. Okay, so here's where my x value tells me I'm going to be, somewhere vertically on this line, right? Because I'm 2 to the right. And then 5 is going to tell me to go up 5. So 1, 2, 3, 4, 5. There is my point A, 2, 5. Now, B is -1, 3. So that means left 1, because it's negative, and up 3 from there. So that would represent my point B. That's how I describe that point. Okay. Now -1.5, -4.5. Obviously, -1.5 is halfway between -1 and -2. So I'm going to go -1.5, which is right in there, and I'm also going to go -4.5, which means down because it's the y-coordinate. 4.5. 4.5 would be between 4 and 5 here. So where those intersect, that is down here and left that much. That is my point right there that I would call C. And finally, the coordinate D is at the location 0, -2, which means that the x value is 0, so we go left and right 0, and the y value is -2, so we go down 2 to this point here. So we'll label that point as D. One side note here that I should have mentioned earlier, but I will go ahead and throw in at this point. We have a special name for the point that is at the center of the coordinate system where the two axes meet, where the x-axis meets the y-axis. This point right here is called the origin. And its coordinates are always going to be 0, 0, because that means you move left and right 0, up and down 0. So that point right there at the center is called the origin. An equation in two variables represents some relationship of two quantities. When we refer to the graph of an equation that has two variables in it, we are talking about the set of all ordered pairs which satisfy the set equation. So for example, if we were looking at, say, either this equation or the one that we will graph here below, when we graph this, we're finding all of the points in the Cartesian plane that satisfy that equation. Okay? So for example, if x was equal to 3, what's the value of y that goes with x equals 3? Right? X equals 3, you plug it in, you have y is equal to 4 minus 3 squared. We've talked about plugging in 4 variables, so I'm just plugging in for x. Now I'm going to evaluate the right hand side by using my order of operations. First I will raise that to the power, so 4 minus 9. That implies, whenever I write the double arrow, I always mean that implies that y is equal to negative 5. So notice, for 3, there is a specific y that goes with it, right? So the point 3, negative 5 is a point on the graph of the equation y is equal to 4 minus x squared. Okay? So if we want to graph, say, y is equal to 1 minus x squared, we are trying to find all the points that satisfy that. Now, if you think about that for a second, you'll begin to realize that that's a problem to do manually, right? To manually find all the points that satisfy that, that means I need to pick every possible x I can think of, plug it in, and find every possible y that goes with it. And I don't just mean integers, like plugging in 1, 2, 3, 4, 5, 6. But what about 1.5 or 1.1 or 1.01, 1.001? Is it possible to pick every possible value for x and plug it in for y and then graph it? And the answer is no, we can't do that. So what we're going to do is make a reasonable approximation to the graph, meaning that we're going to pick a few points. We're going to pick a few values of x, plug them in, see what the values of y that go with them. After having picked those values, we will graph them on the Cartesian coordinate system, or on the rectangular coordinate system, and we'll have a series of points. Okay? Now, if the points look something like this, what do we guess? Well, we guess that in between there's a nice smooth curve, right? Or if the points did this, we begin to see. It's basically what we did in grade school when we learned how to play connect the dots, right? Well, that's all we're going to be doing here. So let's do that. Now, how do we set the problem up? Well, here's what I suggest. You do something called a T-chart, right? A column for your x and a column for your y. And I call it a T-chart because I'm going to put a column in between them and then draw a line across there. So that's my header of my two columns. Looks like a T, right? Now I'm going to pick values here for x and then plug them in. Okay? So what's a good value to plug in for x? Why not plug in 0? Right? That's always a good place to start. So what happens when you plug in 0? You get 1 minus 0 squared, right? Which is 1. So what point is that? That's 0, 1. So on a Cartesian graph, on the rectangular coordinate system, I have now my first point. It is at 0, 1, which means left, right, 0, and up 1 right there. Okay? Okay? What if I plugged in 1? That's 1 minus 1 squared, which gives me 1 minus 1, or 0. So 1, 0. X is 1, y is 0 is another point on my curve. All I'm doing is plotting points. Now, if all I do is plot 2 points, that's not enough to tell me basically what's going on here. I mean, it could be a line like this, it could be a curve, it could be a circle. Who knows what this is going to be? So we need to keep going. So I'm going to plug in 2. 1 minus 2 squared is 1 minus 4, because we've raised the power before we subtract. So that's negative 3. So 2, negative 3 is also a point. So 2 and then down 3. Now notice it's no longer a straight line, right? This thing seems to be curving now. 3. Let's try 3. 1 minus 3 squared is 1 minus 9, or negative 8. So that's 3, negative 8. Over 3, down 8. So there's down 4, 5, 6, 7, 8. Way down here. Okay? Now, it's going to keep going. 4. I get even a larger negative number. So let's assume that we want to just look at this part of the graph. Okay? This is a reasonable part of the graph to focus in on. So we know what appears to be happening on the right-hand side of the Cartesian plane. Now, what happens over here? How do I find out what's going on in this area? Well, I'm going to pick negative x's now. Let's go back and do negative 1. What happens when I plug in negative 1? I did 1 minus a minus 1 squared. Remember, we replace the x with the value. This is one of those places where you got to keep track of that sign. You're going to square the negative 1 first, right? Negative 1 squared is positive 1. 1 minus a positive 1 is 0. Gives me negative 1 comma 0. So negative 1 and then up 0. If I plug in negative 2, I'll have 1 minus a minus 2 squared, or 1 minus 4, which is negative 3. Negative 2, negative 3. Notice how this is now symmetric. Right? It appears to be the same thing happening on the left and right, and the reason for that is the square, right? Because the square of the negative is the same as the square of the positive. What if I plug in negative 3? 1 minus a minus 3 squared is going to be 1 minus 9, or negative 8, just like we had right there. So negative 3, negative 8. Negative 3 down 8. Now what does it look like? It looks kind of like this. You want to connect this with as smooth a graph curve as possible. Now at this point, all you're really doing is guessing. You're guessing that that's what happens in between those points. Now it's possible, by looking at this, that we may have guessed wrong. Already, I can tell you I guessed a little wrong because I didn't draw that very well. But there's no reason to say why the graph couldn't do something like this. Would you expect that to happen? Because all of those points are on the line that I just drew, okay? And the only way to know for sure would be to graph more points. That is, what if I plugged in, say, x is equal to negative a half, and I found it's right here. That now rules out the blue curve that I just drew. All right, so the only way to get a better picture is to graph more points. Now that's one of the advantages that a graphing calculator has, because a graphing calculator is going to plot 25, 50, 100,000 points, however many points it's set up to plot, and then connect those with little straight lines and get you a very good approximation of what the graph is supposed to look like. It can do those very, very quickly. On the other hand, we're going to do them manually for a few examples, just so that we begin to get an understanding of what the graph actually means. Okay, let's get rid of my blue line there and tell you that's the final answer. That's the graph. Okay, you want to plot enough points both on the left-hand side and the right-hand side of the y-axis to get an idea of what the curve actually looks like. I'm going to take the same approach to this graphing problem I did the last one. I'm going to use a T-chart method. I'm going to do x and y, which is what I'm going to ask you to do on all the ones in this section. I can draw some straight lines if I'm on paper. I don't draw very good lines with this little tool that I use to write on the screen, so I apologize for cheating a little bit and using these straight lines when I know by hand you're often going to have to draw these things manually. Now, on the computer, and we will take a look at one example of plotting on the computer so you can see how we would do this. You're not going to be required to plot manually, except to identify which graph goes with which equation, and on the later types of equations where we actually know that it's a parabola or a line or a particular shape, we may be able to use those tools that are on the graphing utility on the computer homework. And so we'll take a look at that before we close out this section. Y is equal to the absolute value of x plus 1. So pick 1. So y would be equal to the absolute value of 0 plus 1, right? Which is clearly 1. So that's the point 0, 1. 0, 1, it's right there. Okay, plug in 1. Absolute value of 1 plus 1 is 2. So over 1 up 2. Plug in 2, absolute value of 2 plus 1 is 3. So that's over 2 up 3. You begin to get the picture, hopefully. It seems to be going in a straight line. Absolute value of 3 plus 1 is absolute value of 4, which is 4. So 3 up 4. So that's this line right here. If I can get that go right through those points, that would be even better. All right. What's happening on the left-hand side? What if I plug in, say, negative 1? That's absolute value of negative 1 plus 1, which is 0. So negative 1, 0 is a point. Negative 2. Absolute value of negative 2 plus 1. Now here's where things change. Negative 2 plus 1 is negative 1. But the absolute value of negative 1 is positive 1. So I'm at negative 2 up 1. If I plug in -3, it's -3 plus 1 is absolute value of -2, which is +2. So over 3, left 3, up 2. And what do you see happening is this thing is going back up. If I went one more, -4 plus 1, it's going to give me a negative or +3. It's going to be right up here. Sorry. That's left 4, up 3. Okay, and so this thing kept going straight in until it hit a value that made the inside negative, and then it started going up here. And so we have this shape right there. It keeps going that way. There's the graph of that equation right there. Here is a sample problem that you would see in your homework, your online homework for this particular course. It asks you to graph the equation, and the equation is given here, y is equal to 3x squared, and it's telling you, let's plot it at the values of x, -3, -2, -1, 0, 1, 2, 3. And so you're going to fill in the t-chart here. All right, so if I fill in a series of values, I'll do these pretty quickly. We'll just do them in our head, right? 3 times -3 squared is 9, so 3 times 9 is 27. Okay, check. Nice work. -2, so 3 times -2 squared. -2 squared is a +4. 3 times 4 is 12. Check answer. Fantastic. All right, -1, so that's going to give me 3. Woo. 0, give me 0. Whoop-de-doo. 1, I think it's going to be now symmetric, so it's just going to go 3, 12, into 27. All right, now, next phase. Here's a picture. Now, you got to identify which of these represents these points that we have. So -3, 27, so -3 up 27, -2 up 12, -1 up 3, 0, 0. The best fit of these would be this value right here, right? Because if I'm going over and up, over, up, over, up, and then over, up, over, up, over, up, that's this graph right here. So A. Check answer. Excellent. All right, there you go. That's how you're going to be graphing these things on the homework. Okay? Does that make sense? All right, last thing we're going to take a look at is interpreting some graphs from some word problems, being able to use these graphs to answer some questions. All right, so here we go. This is taken out of your textbook. We are given a graph that says, well, here's the problem. When a person receives a drug injected into a muscle, the concentration of the drug in the body is measured in milligrams per 100 milliliters. Depending on the time elapsed after the injection, measured in hours. The figure shows the graph of drug concentration over time, where X represent time in hours and Y represents the drug concentration at that time. During which period of time is the drug concentration increasing? So as we go from left to right, when is it going up? When is the drug level increasing? Notice as I go from left to right, starting at 0, it increases until I hit time equals 3, right? So from 0 hours until 3 hours, it's increasing. Now, during which period of time is the drug concentration decreasing? Well, from that point on, right? From here all the way on, it's decreasing. Okay? So it goes all the way up to 13. So I could either say for x greater than 3 or from x equals 3 until x equals 13, because we don't know if this graph continues on by this model. Is it infinite or not? So obviously we're not going to do infinite time. Since it goes up to 13 hours, we'll say up until x equals 13, or from 3 hours to 13 hours. The important thing is that you understand the concept here. Now, what is the drug's maximum concentration? When does that occur? Well, clearly that's this point right here. Okay, so the maximum concentration is y is equal to 0.05, right, this height here, and that's in milligrams per milliliter, and it occurs at x is equal to 3 hours, so after 3 hours. And what happens by the end of 13 hours? Y goes to 0, right? 0 concentration. Because as this thing decreases, it eventually hits 0 right there, and then after 13 hours, the drug concentration remains at 0. Okay, so that's what we can get from looking at a graph representing this particular model. All right, that ends section 1.3.